So I want to really thank Park Systems for hosting the event today. I've been working on this idea in the background for a while now and never really gave it much thought of what the name should be. Once I get invited to the symposium, it kind of jumped out as kind of obvious. If you could imagine two machines, identical, put one at the North Pole, one in Egypt, they'd have different operational characteristics. If you had a physically accurate computer model, you got to hit the fast forward button, you could see how one might fail in a way that's different than another one, and that would empower your customers to know if they should order certain report parts, et cetera. That physical computer model is called a digital twin. So the concept of digital twin microscopy is related to that. Emin recently left an extended leave of absence in industry to return to academia and the nuclear science group. So once you get to the nano and sub-nano scale, observation becomes kind of difficult. So the concept of a digital model to pair with microscopy is quite interesting. So I'm in the group of Dr. Emily Liu. Her expertise is nano to mesoscale physics. And like I said, we're trying to go deeper and penetrate smaller into the atomics. So this is where it started, where it kind of came from. I was working on thermodynamics in industry. This is just a representative sample. We talked earlier about climate change and those challenges. If you're doing energy balance of our heat engines, you'll see that the bulk of the energy that we cannot capture is in the form of waste heat. The traditional method to go after that is to put an additional heat engine to try and capture it. That becomes complex and expensive very rapidly. So the thought I had was like, is there some way we could just go after the heat directly? And that's where we go here. So if you start to get below the nanoscale and quantum physics effects become real, or relevant, I'll say, it gets very convoluted quickly. So not going to go through these specifics, but basically the electrostatic charge, if you focus on that alone, you get to ignore a lot of the uncertain aspects that you're normally saddled with. So the rest of the talk is going to be based on that one assumption. So simplistically, you think of every point in space as the electric field. Every point in the electric field is a function of every other point in the electric field, positive or minus charges. It's just basic physics 101, freshman class, maybe high school level physics. And so what I wanted to do was say, could I model hydrogen and pair it to some of the more complex wave equation functions? If I could do this in a very computationally efficient way, this could maybe get me excited about trying to go to a more robust digital twin model. So just sitting on a spreadsheet in Excel, typing out that equation we just showed, doing an array. You can see the equation of the spreadsheet. It's just basically each cell is at a grid location, XY axis. No real complex physics there. Making the spreadsheet, I want to zoom out to make sure my formatting was relevant. It's kind of hard to see here. Maybe you can't see it, but near the center, which was the 0 point, you could almost start to see the electron. I thought that was kind of interesting, but I didn't really care too much until I switched the slide, and this is the proton. So I thought something was wrong at first, because why would the proton electron be different? The only thing is the -1 charge in my assumptions. And then it turns out Excel auto-formatting, the minus sign takes some of the character space, so it just formats the sheet differently. So again, I wasn't too interested in it until what I did next was I take the origin of the electron cell plus a 53 cell offset from the proton origin, and that will superimpose what hydrogen looks like. That's the atomic radius of hydrogen. And then this is what I saw, and again, like if you're like me, it was kind of hard to see, but I saw something, and I wasn't intending to see anything. I was still kind of stuck in the mathematics. So this caught my attention, and I wanted to figure out if there was some trend analysis I could do. So zooming in, I noticed, it's hard to see here as well because it doesn't catch your eye, but as you scroll through the hundreds and hundreds of cells, the formatting actually is visually attractive. And what I did here was just highlighted some cells to say they have less numbers in them physically, so there's more white space. And as I was highlighting them, I could see a pattern start to emerge. You can see this is plus or minus 8 are the blue cells, and it's symmetric across the center line. Same thing with the orange. So I spent a lot of time formatting the spreadsheet. And just there's my color code there. If I had one single digit, I made it black. If it didn't go to scientific notation, but it was negative, I colored it orange, green if it was positive. I discovered, I wasn't expecting, the center line was going to be 0. And then at the 0th row, for every column, that was actually the maximum value for that cell. I also wasn't expecting it. And I was just bored and doing this in the background. And I wasn't too excited until I did this. And zoom all the way out. This is what my spreadsheet looked like, just using that simple equation. And if there are any electrical engineers in the crowd, I found this to be very interesting. Because early in my career, I learned about the right-hand rule for motors and generators. And I never understood why it was the way it is. So if you don't know that, if you take a charged particle and you put it into a magnetic field, it will travel in the direction of your finger. And so I'd asked the question before, why is there an inherent perpendicularity? And maybe there's an answer and I just wasn't exposed to it. But for the first time I could see, I'll flash back, just by putting two opposite charged particles in proximity, the inherent perpendicularity emerges. So at this point I was like, oh, this is pretty exciting, I'm going to keep going. So I revisited the equation. I made it more general so that I could do multiple charges, et cetera. And I asked what would happen if I could see a more complex atom. It's the same basic structure, but I had to get real data at this point. So going to the internet, to the other databases to find what is the atomic radius. This is the spreadsheet I used. If I have one electron, right, we're corresponding to the different atoms. So this is the different radius, and that's how I kept track of what I was doing to model different atoms. And so what you see here is essentially some snapshots of my array. Essentially, if we could imagine, we're looking at a cross-section of an atom, and we're starting at the negative 250 mark, and we're flying towards the atom. This first cell goes from negative 250 to negative 44. And these are the electron grid points, so to speak. This is a carbon atom. And I use conditional formatting, and here's the answer key for that. So the highest values, not necessarily positive or negative, but the maximum values in the array are red. The lowest values are black. And then if it's a generally negative or generally positive, that's the different colors there. So you don't see anything change until you get around negative 44. And then the negative fields of the additional electrons start to emerge. And as you get closer, you can see the nucleus will begin to look positive instead of negative. And as you get close, you can see the inner ring electrons around the atom. So then doing the same thing for neon, and again, using some geometric reductions to find minimums at the radius, et cetera. Zooming in from negative 250 to 95, you don't see any changes. Once you get around negative 63, the electrons will start to diverge into their actual points in the grid. And as you continue to get closer, you see a unique arrangement of negative and positive fields. And then I thought, well, that's pretty cool, but I don't know what to do with it. What if one of the electrons gets ionized or taken away? What happens? And so here I'm just doing the one comparison of neon, and I've taken away or ionized or whatever, removed the electron at this grid location. And so this is a before and after. So we already saw what it looks like. Take one electron away, the entire field becomes positive. So if I'm an electron and I'm just free and floating in a breeze and I see this, I'm going to stay as far away as possible because it's all repulsive to me. But now everything is very attractive. And then as I get closer, you'll see even when the electron field stays negative, that vacancy site is still very positive. It's going to attract the electron. And then same thing, as you get closer into the center, the positive nature of the field with the absent electron will attract every electron that's in the region. So that's all well and good, but it's basically me just on my spreadsheet on my desk. this and other things encouraged me to go back to academia and put some academic rigor into it. And so what I'm working on now and some next steps is to make this computationally efficient and connect it to a LED grid array. And so once this is done, we should be able to see the full array. Now we're limited to like a cross-sectional slice, which isn't very exciting or good for studying the inner workings of an atom. But essentially, once we're at this level, there is fundamentally computer speed and memory is the limitation of how big of an array and how complex you could model. And once you add all these things together, you could zoom in, zoom out, do different scenarios, et cetera. And then assuming this ever gets to a level of maturity and we validate it in a way mathematically, we're going to need some type of real-world validation. And that's where the concept of digital twin microscopy becomes real. And then I'll apologize for not including some more forward-looking information, but I will say my ears have been wide open. I've heard a lot of things that have excited me about how this could be used in an industry where understanding vacancy sites and dopings and defects, et cetera, having ways to maybe better identify where they are and then go into the real world with the technology to find them. I was excited to attend today. And this is more of the same, but basically that's the future work. To add the time domain. Now it's just a static array. You put in some locations of charged particles, but working with some computational experts at RPI, we're working on discretizing the time domain equations to get a array that you could hit play and watch how things work in real time. And that's it.
Open for questions. I have a question. You started with all this electron orbital density force, then expanded to multi-electrons, and you have all this density map out. How is that connected to, you said LED? I could not make that connection.
Okay, so at the beginning, I was simply trying to figure out a way to computationally see more efficiently, like Schrodinger's equations, et cetera, are these complex coefficient-based equations. So I was seeing if we could make some simplifying assumptions. And so through a body of work I'm not presenting here, I down-selected just the electron charge. And I was expecting to go down a path of continuing that work, but once I saw this, essentially, it occurred to me that nuclear engineers are investigating blind, right? Imagine trying to cure infectious diseases before the microscope was invented, right? It was very difficult. So that's how I felt. So I began to focus at that time on the visualization aspect of just the simplified physics. So I took a detour to make a more robust set of simplified equations into a 3D array to still eventually get to scaling up into where I was trying to go. But I wanted to have and I still want to have, the strength of a visualization 3D array so I could see how these things are operating together. So this is now, in my mind, a puzzle piece or a magnetic piece of positive and negative charges, where in space they can maybe self-align. And so if we have a time-dependent computer model with an LED array and I can watch my simulations, I feel that's much more empowering than trying to hunt and peck through spreadsheets. So it is a nonlinear path, you're absolutely correct. But once I saw the power of the visualization, that became the primary path.
Any other questions?
Yes?
So have you looked at other, like how this compares to other chemistry modeling software? What's that?
So what I've looked at is if you go into the shell model equations and the different snapshots, I can show correlation. The reason I haven't focused on, I have looked at software, and the reason I walk back away from them is they're very coefficient based. And a lot of these coefficients, same as heat transfer chemistry, no matter where you look, at the nanoscale, they start to get marred by the uncertainty we talked about earlier. So I'd classify those softwares as big to small physics, where this attempt is trying to go from small to big, just building up what we need and including them as they're required.
It seems like you're taking oversimplifying.
That's what it seems like, but to date, I found no valid reason to reject the hypothesis. I may find it. I'm still looking, but so far, yeah, I'm excited that it, as robust as it is, being so simple.
I'm just curious, why rubbing it is the one relation generated an AC current, whereas you did circular, generated a DC? Any theoretical experience?
No, I have no theoretical experience with that.